Let's look at some examples of relations and decide whether we have symmetry, reflexivity, let me list them in order that the chapter does, reflexivity, symmetry, and or transitivity. Okay, so take a look at this first relation. Remember, all relations are collections of ordered pairs of elements from some set. So what set is this a relation on? Well, I can see that the elements in the ordered pairs are the numbers 0, 1, 2, and 3. So with such a small amount of elements, it may be helpful just to sort of write those elements down. So this is the set A, the set of those 4 numbers, and the relation I can express with some arrows. So saying that 0, 0, or 0 is related to 0, 0, 0 is in the relation R1, I can demonstrate that by drawing a line like this. So 0 is related to itself. Similarly, 0 is related to 1 can be drawn like this. 0 is related to 3. 1 is related to 1. 1 is related to 0. 2 is related to 3. And finally, 3 is related to 3. So this diagram right here gives us a visual of the relation R1. Let's check the properties of reflexivity, symmetry, and transitivity one by one. So reflexivity would say that for all x in A, x is related to x. So R1 is standing for the relation. I'm writing the character R for reflexivity. So is it the case that for every single number in A, 0, 1, 2, or 3, that number is related to itself? Well, the answer is no. So R1 is not reflexive, and that's because 2 doesn't appear to be related to itself. So I can say it like this: 2 is not related to 2, or I can say 2 comma 2 is not in R1. Okay, let's check symmetry. So in order for this relation to be symmetric, this is what I would have to observe. For all x and y in the set A, if x is related to y, then y is related to x. Let's take a look. I do see that 1 is related to 0 and 0 is related to 1. I do see that 0 is related to 3, but 3 is not related to 0. And actually over here I've got an issue as well. 2 is related to 3, but 3 is not related to 2. So to demonstrate that this relation is not symmetric, all I need to do is break this for all statement. I need to provide an example of a pair of numbers in A such that x is related to y, but y is not related to x. So I'm going to write that out. R1 is not symmetric. And here's my demonstration. Note that, for example, 0, 3 is in R1, but 3, 0 is not in R1. All right, there's my demonstration. Finally, transitivity. Let's recall what we would need to have in order for R1 to be transitive. Anytime R is related to Y and Y is related to Z, I must have that X is related to Z. Let's check it out. You just got to kind of look at all the arrows and see what you can find. I do see that, let's see here. 1 is related to 0 and 0 is related to 3, and yet 1 is not related to 3. So I think I've found that R1 is not transitive either. So R1 is not transitive. Again, breaking transitivity is somewhat like breaking the others. I just need to demonstrate a situation where this part of the conditional is true and yet the conclusion is false. So I'm going to go ahead and do 1, 0, and 3. So note that 1, 0 is in R1 and 0, 3 is in R1, but 1, 3 is not in R1. Okay, there you have it. This relation is not reflexive, not symmetric, and it's not transitive either. I've just went ahead and modified these two relations slightly, I've modified relation number 1 in 2 different ways. I'm going to draw the diagrams real quick, and then we're going to check the properties one by one again. All right, so I've modified the original relation in a couple different ways, and I want to test to see whether I have reflexivity, symmetry, and transitivity, just as I did before. Let me change all these to 2s here, and then at the bottom, we're going to test relation number 3. Okay, so I sort of like added some points and removed some points to make these 2 different relations from R1. And I've drawn the appropriate diagrams to represent. So in R2, I've just added 2 edges, and I want to see, what properties this relation has. Still, R3 is not, or pardon me, R2 is not reflexive for the same reason as R1 isn't. I don't have the 0.22 in there. So R2 is not reflexive. 2,2 is simply not in R2. Symmetric, let's see, I still think that this relation is not symmetric, again, for the reason before. I've got 0, 3 in there, but I don't have 3, 0. So R2 is not symmetric. Let me just say as before. But I do think that I fixed transitivity. So take a look. This is a little bit subtle. You have to focus on what transitivity is saying and what it's not saying. So I have to check transitivity, I have to check that whenever I have this arrangement, that is x is related to y and y is related to z, then I'm guaranteed to have x related to z. That doesn't say anything about the existence of a bunch of edges between any pair of points in the graph, though. All it's saying is if you have an edge from x to y and an edge from y to z, there must be an edge going from x to z. So check it out in the diagram. I do have 1 related to 0 and 0 related to 3, and I've added in there that 1 is related to 3. So in the set itself, I've got 1 related to 0, 0 related to 3, so those satisfy the 2 parts of the front end of the conditional, and lo and behold, I do have that 1 is related to 3. So in that instance, the sort of transitivity is okay. For example, 2 is related to 3 and 3 is related to 3, and hence I do have that 2 is related to 3. That's technically a situation where this conditional would be true as well. But it's never interesting when one of these relation fragments is like 3 is related to 3 or 0 is related to 0. Let me just do one more to demonstrate that that's the case. So 0 is related to 1, and 1 is related to 1, and 0 is related to 1. That also satisfies this conditional. So when all is said and done, I have checked every single instance where I have this statement being true between 3 points, and the conclusion of the conditional also remains true. So I have checked the transitivity is true for this relation. So R2 is transitive. It's too much to write all of those out here. Looking at the diagram, we do see that that's the case. All right, let's move down to this next relation here. I've actually fixed the reflexivity of the relation. So you can see for each element in A, 0, 1, 2, and 3, x comma x is in R3. So in other words, x is related to x for every single x in A. So R3 is reflexive by looking at the picture or observing that, that this holds true. What about symmetry? Nope, I still do not have symmetry here. R3 is not symmetric. Again, 0 is related to 3, but 3 isn't related to 0. And there's a couple other problems in there as well. So is not symmetric as before. And maybe this is the most subtle one of all of them. This relation is transitive. The point is that, the front end of this conditional is just very rarely satisfied. So, take a look. 0 is related to 1, but 1 isn't really related to anything else. So I don't really have a 0, 1, and then 1, and then some other number to check. I do have 0 is related to 1, and 1 is related to 1, but as we've noted before, that easily gives us that 0 is related to 1. So the conditional is true when either one of these fragments is a double. But yeah, you're not going to be able to find an arrangement of 2 arrows sort of in sequence at all in this diagram. So there's really nothing to check. This is almost vacuously true if you're ignoring the loops in the graph. So R3 does end up being transitive. Okay, and that's simply because every single time this arrangement holds true, the back end holds true as well. Okay, so when your set A is small enough, these diagrams are useful in checking these three properties. We're not always going to have that situation, so we have to think about the properties logically. Let's go ahead and run through a couple more examples and just analyze these relations as to whether they're reflexive, symmetric, or transitive. So the set here is the power set of some non-empty set. I mean, that's a set that we're going to define the relation on. So this relation, which they're calling U, it's not a union or anything, it's just a symbol that's standing for a relation, is defined in the following way. So we're going to call two subsets of X related to each other if they're not equal to each other. It's a weird thing to define, but that's what we're doing. So again, the power set of X is the set on which the relation that we're defining lies. And given any two elements of that set, we define relation if the sets are not equal to each other. Okay, so let's check reflexivity. I claim this U relation is not reflexive because, for example, I mean, take a specific element of the power set of X. How about X? X is an element of the power set. The empty set is also an element of the power set, if you like. Oh, sorry. Wait a minute. N power. Let X be a non-empty set. Oh, yeah, sorry. Yeah, the empty set's also an element of the power set. What was I saying? So here's the thing. X is definitely not related to itself via this relation because X is not equal to itself. X is equal to itself. So that's the opposite of being not equal to itself. So U is not reflexive. Symmetric, yeah, actually it is. U is symmetric, and you just got to think about it for a second. If A is related to B, then what that means is that A is not equal to B. But that means that B is not equal to A, so B is related to A. This is super awkward because my U is looking like a union. I'm just going to come back and put a little curl on it or something because I don't want it to be confused with the union symbol. So let's imagine that they have used a better symbol for their relation. Okay, finally, transitivity. Transitivity. Pause the video, but I don't think that this is transitive. So this is not transitive. Oops. I have an example in mind. I'm going to go back to the set X and the set empty set, which I know are two different elements of the power set. So observe. Note that, let's see here, empty set is related to X because these two sets are not the same. It's given that X is a non-empty set, and X is related to the empty set. I've just stated the same thing in a different way, but they're both true statements, and yet, so if this relation were to be transitive, I should be able to conclude from this that empty set is related to the empty set. But that's not true. Empty set is equal to the empty set. So I have that empty set is not related to itself. So that proves that this relation is not transitive. Okay, so we have to be able to deal with these three properties in situations where we don't really have a good drawing of the relation or the set that it's defined on. This is just a very abstract thing. I'm just arguing from the definitions. All right, same with this. I've got this sort of example given to me in words. The set is all the people living in the world. Great. And we're going to define a relation on that set. P is related to Q if P lives within 100 miles of Q. So go ahead and see if you can figure out whether this relation is reflexive, symmetric, or transitive. Pause the video and come back. All right, what'd you decide? Reflexive, yes. Everybody lives within 100 miles of themselves. Yes, people, let's say each person lives within 100 miles of themselves. Okay, symmetric. Yeah, I think so. If I live within 100 miles of you, then you live within 100 miles of me. Let me write that out. And finally, transitivity. No, I don't think so. I mean, I'm going to draw a little diagram here. Let's say person P does live within 100 miles of Q. Let's say they're like 95 miles apart. And then maybe just in a direct line, Q lives another 95 miles away from a person S. Then, if this is a straight line, P lives way further away from S than 100 miles. So this relation is not transitive. So P can live. Okay, there you go.